Good afternoon, students. This is Dr. Ravi Kant here, and I will be assisting Dr. Vinay Vakharia in order to uh, do this experiment, uh, namely dynamic simulation of drone using MATLAB Simulink. The package is called Simulink. This is the second experiment for Mechanical Engineering Department for Industry 4.0. The aim of this study is to this particular experiment is to study the dynamic simulation of 2D drone model in a software called MATLAB. Most precisely, we will be taking a plugin, MATLAB plugin known as Simulink, which is an additional plugin. You can uh, see in your regular MATLAB software. In this is a package where you can actually simulate your dynamical system. In this particular experiment, we are going to um, do the dynamic simulation. What does it? What do you mean by dynamic simulation? Uh, we are going to study it, if at all. Let's suppose you have. Let's suppose you have. Let me. Let's suppose you have a quadcopter and it has propellers. Right. Let's suppose it has four propellers, but in this particular study, we are going to take up the two-dimensional case. So let's suppose uh, our coordinate system is such that we have y-axis here, z-axis down, and x-axis is into the plane of the paper. Okay. But we are going to study in two-dimensional case in the yz plane. This is the orientation, any generic orientation of the 2D drone. And at any moment of time, it, it will exert any generic force u1. I'll talk u1 uh, will tell that this linear force that it, it is in the orientation, any generic orientation, it is denoted by u1, and the twist or the moment that is acting due to these propeller effects, it tries to twist it, and this twisting effect uh, has the moment called u2. So u1 is essentially a force and u2 is essentially a moment or torque. Okay, so now uh, we can apply Newton's law to find the governing equations. um, Associated with two-dimensional drone. We can actually break up this linear force. So we can actually apply uh, the Newton's law in linear form, which states that summation of all the forces will give you mass times acceleration. Okay, and the second equation is summation of all the torques is nothing but I times alpha, which is the angular acceleration. Uh, One more thing. So this acceleration in linear acceleration can also be seen as a component in z direction and in y direction as well. Okay. So let's suppose this angle the current angle that the drone orients at is phi currently. Okay. So we can apply the Newton's law in the component form, which states that summation of all the forces in x direction will lead to mass times acceleration in x direction, and summation of forces in not in x direction, maybe in z direction. Sorry, z direction, because x direction is not considered here. It's been not considered here. So f, and the second direction is y direction. So summation of all the forces will give me mass times acceleration in y direction. And the usual torque or the moment can be written as I times alpha. Alpha can also be written as, this is angular acceleration. This is the angle phi. So I can write d2 phi by dt square, or I can write I phi double dot. So the dot sign will be represented here to denote the uh, second derivative sign. Okay. So let's take the first z direction. Uh, um, linear momentum conservation. So summation of all the forces in z are, gravity is acting in minus in z direction, downward it is acting, we have taken it positive. So let's suppose this force u1 is acting. So in x direction, the component that will act in x direction would be u1 cos of phi, right? And in y direction, the component would be u1 sine phi, isn't it? So let's take one by one. So u1 cos phi is here. So what I can write here is, because of u1 cos phi, I will have mass times acceleration in z direction. So acceleration in z direction. Let's suppose the displacement happening is z. So the acceleration would be d2 z by dz dt square, right? So I can also write it at z double dot, mz double dot. But there is an there is acceleration that is happening in, so there is a force that is also acting on this quadcopter, that is mg in positive z direction, right? So this is, so essentially, so this, since this we have put zn down as positive, so we should write this way. So mg minus mz double dot, or okay, let me write it properly. Z double dot can be written as mg minus u1 cos phi, or let me divide m throughout. So z double dot is equal to g minus u1 cos phi divided by m is my first governing equation. But this governing equation is non-linear in nature. we need to linearize it in order to uh, design the controller, because it would be advantageous if you uh, make your governing equations in linear way, because it is easy to design the controllers if your governing equations are linear in those regime. So for small angles, we can approximate for small angles. Your cos phi is close to 1 and your sin phi is close to 5. This is what we know. That is why the approximated z double dot governing equation can be written as g minus u1 phi, sorry, phi, and this is cos phi here, u times 1 divided by, this is your first governing equation. Similarly, in y direction, also we can write the Newton's law, summation of all the forces we have acting is u1 sin phi, and this gives it the acceleration in y direction. So there are no other body forces. So I can directly write m y double dot, right? So y double dot I can write u1 sin phi by n, and again with the linear assumptions with small angles, I can write this as u1 phi by n. So this is your second equation. Okay. And which is precisely stated in our manual as well. Z is equal to this much. In non-linear, y double dot is this much. Now let us talk about the preservation of angular momentum. That is, summation of all the torques is equal to moment of inertia, that is Ixx, times the angular acceleration alpha, which we have already denoted as y double dot. So we have only the torque that is at here only is u2, which is equal to Ixx times y double dot. So that is why I can write y double dot as u2 by Ixx. This is my third equation. So now we have three equations in hand. This one, and this one. Notice that things are coupled in nature. So this partial differential equations, or not partial. Uh, these three ordinary differential equations, because these are not partial. Ordinary differential equation differentiated with respect to time are actually coupled in nature. That is why the dynamics of drone is quite complicated. You can see z double dot is over here. You have phi over here. This phi is again a variable, and which phi can be estimated. Phi, the information of phi is coupled from this equation. Now the data here given here is g is equal to 9.81 in appropriate units, it's meter per second square. Mass of, let's suppose the drone is given is 0.2 kgs, and the moment of inertia about its axis, this axis into the plane of paper, is given as 0.1 kilogram meter square. So with these data, we are going to make a Simulink model first, and let's try to simulate what's happening. So what is the overall idea of simulating the dynamical system? So you should have information at the end of this simulation. You should have the information of y with respect to time in your hand, z with respect to time in your hand, and phi with respect to time in your hand. So all this information you should have. How your y is going to uh, evolve in time whenever you are giving some certain input. The certain inputs can be step input or maybe impulse or maybe ramp input or anything. But just to start with a simple case, we'll take step input. Uh, so what is the meaning of step input, giving step input and seeking the information? So let's suppose this is your drone, or maybe this is your drone. Let's suppose this is your propellers. It is rotating and it is giving a lift. So my y direction is this way, or z direction. Let's suppose I'm giving z direction at certain input. So I have uh, given a function, a step function, or maybe a sub impulsive function in z. So z with respect to time. So this is your time axis. So I'm so before this particular point, we have no information of z, or maybe z is 0. But after that, we have given unit jump to z. So probably maybe 1 unit, 1 meter I have shifted. Okay. So how this particular guy would respond to this particular input? Not only in z, we can actually try to rotate it with some angle, maybe some unit step. I could give as unit step input in the angle as well. I just wanted to twist it in certain way, and then I want to see how it behaves. Okay. And this would be our first step, and the second step is to design PID controls. So actually, this particular lab is we cannot finish everything in one hour, but you need to just I'll give you a brief overview of what these PIDs are. So this PID, the full form of PID is proportional, integral, and differential control. So based on the error, uh, feedback error, it is going to give a input, a control input in that manner, in order to get things. I mean, let's suppose I am giving a jump in this fashion. So whether you are going to I mean, your response, this is your input and this is your output. There is what response you could expect. Okay. So this response can be controlled by these PIDs. So whether I want a springy response, or I want a overdamped response, or I want a critically damped response, these all can be decided by the PID controllers. Okay. We are going to design that also. But first, let's simulate y, z, and phi with our Simulink model. So in order to do that, let me unshare uh, this PPT here, and let me be uh, sharing my slide from my laptop, where I have already installed my MATLAB Simulink. This is the typical interface of MATLAB would look like. I have already finished the model, but since this is an introductory class, I am going to make the model from scratch. So what you have to do here is uh, there is a menu toolbar called Simulink Library. You have to click on that. Okay, so in the Simulink toolbar, this is called Simulink Library. There are all sorts of libraries are there. There are commonly used blocks such as constant, gain, input, output, sum, scope. Scope is where you can actually see your plots, how it is, how your dynamics is changing with time. Okay, all sorts of blocks are there. So to start with, let's make a new model. New model. Type file new and model. So what you are going to do is you are going to put it side by side. So first we are going to simulate our uncontrolled 2D drone plant in ceiling in with the information of these governing equations. So what I will do is let me start doing it, and in the meantime I'll try to uh, I'll try to tell that how it is related to the governing equation. So we will start with this particular equation as z double dot is equal to g minus u1 by n cos phi, or uh, cos phi would be 1. So this won't be here. So just g double dot z is equal to g minus u by m. So we start with any gain that is g or 9.8. I will subtract it with uh, any step input or any input, and I will multiply it with a gain that is 1 by n, and then whatever the thing that will come, I will treat it as z double dot. Okay, so this is how I'm going to draw this in Simulink. So let's start with a constant gain or constant whose value would be 9.8. So what you have to do, you have to drag and drop things over here. Drag from this place, from library to the working place. So currently the value of constant is 1. We can double click it and we can change its value to 9.8. Apply OK. And it is also customary, and it should be a good practice to write things. So this is my G over here. So I can write G. This is my G. Now what you are going to do is you are going to give any input. So this Z, and this should be subtracted by some input times 1 upon it, right? So what I will do here is I'll take some input. Let's suppose I have some input. I'll tell that this input is my U1. This U1 is going to be multiplied with some gain. Okay, so this is my gain. I'm going to drag and drop over here. This gain I'm going to write 1 upon. So what is my mass? 1 upon 0.2. Mass was 2. Apply. This is this. I'm going to write this gain as 1 divided by m. Right? So we are going to connect it. So just connect it to drag and drop. Now we are going to subtract whatever the thing is coming. So this u1 times 1 upon m has been multiplied, and this signal is going to be subtracted with this g value over here. So the subtraction can be done through this sum block. Okay. We are going to connect this properly, but be careful that these signs over here, both our signs are positive. We are going to make this sign as minus and plus. Minus and plus. Right? So this u1 times 1 upon n is going to be subtracted by your g, okay. And whatever the signal that is coming out, it is what is this signal? Z double dot, right? So I will write Z dot dot, or I will write Z dash dash. Okay. This signal is Z dot dot. Now since we need the information of, so that is what this is acceleration. We need the information of velocity of the displacement also. So we are going to integrate it. Okay, so integration, we have the integration also, integration blocks also. In continuous you have integrators. So I'm going to integrate it. So we'll put an integrator over here. And I'm going to connect this with the integrator. We have to just drag and drop. Okay. So now it has been integrated. Whatever the signal that will come out. This is my first integrator. So whatever the signal that will come out of from here would be your Z single dot. Right? We have integrated. So we can integrate it once again. So we can again drag and drop and put things here. Okay. Now the signal that will come out from here would be simply Z. We are not going to we can actually put a scope over here to see what is the dynamics that is happening, but right now I will stop it through some source block, sorry, the sync block, the out block. The reason of putting out and in block is to, I will make a subsystem over here so that your model should not look clumsy. So this should look something like this. So this is a single block that inherits u1 and u2 as input and z, phi and y as your outputs. So in so all this whole block uh, is being clubbed or is being associated with these clumsy things over here. So this all these things are clubbed into one subsystem, and it has been this one plant, single plant has been made. And once this has been created, I'm going to put a step function on u1 and u2, and we can see the dynamics of z, phi, and y simultaneously. Okay, we can do that right now. Not this one. This was my word. This one. Okay. So as long as we have figured out your z, now let's talk about u2 and your phi's and y. So let us go through the governing equation once again. So y double dot is what? u1 by m1. And your phi double dot is u2 by ixx. So what I will do it, we will take up this particular guy first. Phi double dot is u2 by ixx. So what I am going to do is I am going to input another form of input. We call it u2. I will multiply it with 1 upon ixx, and I will tell that whatever the signal coming out here would be phi double dot, and then I'm going to integrate it. I'll write that as phi dot, then I'm going to integrate it once again, and then I'll call it as phi, and this phi can be thought to be coupled with this particular equation. I'll show you how I'm going to make it. So let me start with another input, and I'll call this input as U2. Okay. So U2 I want to multiply it with 1 upon Ixx. So 1 upon Ixx, so Ixx is 0.1, which we have already decided, and this I'll call as 1 upon Ixx. So I'm going to feed the signal into this game. Whatever signal that is coming out of over here is directly my phi double dot. Okay, so I'll write here phi dash dash. Okay. Now I'm going to integrate it. So integration is in continuous block integrator. I'm going to integrate it. So whatever the signal that will come out here is phi dash, that is the angular velocity. This is angular acceleration, phi double dot, and phi dot is the angular velocity. Again I can integrate it, and I'll get what? I'll get the phi income. Now you can see that we have already let me go. So you have the phi information. Now if you have the phi information, because sine phi at a small angle is phi, so this phi can be written directly as phi. Once again I can multiply it with some gain. Okay, what I will do is I will make the output over here, one output here over here as a phi. I want this phi to be as in one output. Once again I will multiply it with one gain. So what is that gain? That gain is 1 upon n. This gain is 1 upon n. So this signal coming over here can also be branched out. This phi can be branched out and can be multiplied with gain 1 upon m. M is 0.2. Okay. And maybe we are doing some. Okay, fine. So this 5 times 1 upon m will give you the information of y double dot. Okay, so this is your y double dot. Now I'm going to integrate it, and the signal that will come out would be y dash. Okay. And again I am going to integrate it with, and then I will get y information. So this will be my y. So I'll take one more output. So this, it has 1 and 2 out inputs, and out 1, out 2 and out 3 as Z, Y and Y. What I am going to do is I am going to select all these, make a right click, create subsystem from selection. So it will make a one subsystem like this. Okay. So we should write here U2. This as U1. It will all automatically be reflected there. This is my Z. This is my phi. This is my Y. So it has been reflected over here. Okay. So this has 2 inputs and 3 inputs. Right. Now my plant is ready for to deploy. You can see the dynamics. So now what we have to do is we can actually get rid of these things, and we can obviously this is already one, so we can uh, uh, place a step input over here. So this is only this will be in source and sync, probably in sources. Yes. So we have assigned a step input. So step input I will keep it here. One more step input I will keep it here. And out I will delete it. And I want to see the reference to the scope. Okay, so scope will be in the sync. Scope is kind of thing that you can actually visualize. I can place 3 scopes over here. Now let me so step input is defined as 1. Okay, let us run this Simulink model and let's see what happens. Before that we have to save this file. I'm going to save it as test 1. Okay. Now I'm going to run this file and let's wait for the simulation. Now it is ready. Now we are going to see the scope, what has been, what is there. See, your plant is unstable. You can see from here. I can rescale it. Obviously, the plant is unstable. So whenever you are giving step input, so let me what whenever I have given step input, it has keep on increasing. The graph has kept on increasing drastically, and the plant is unstable. So probably to give you a feel of what actually is happening here. So let me plot the step input and the response in, in parallel. So for that, what I will do is I'm going to use Mux over here. So what it will do is it will give you a comparative plot between. What I will do is here, I will delete this guy over here. I put the Z over here, and one Z I will take it from the step signal. So essentially, uh, Your step signal will also be plotted here, and your output Z is also plotted here. Similarly, with this here, I'll put a marks over here. I'll place a phi over here. I'll place another phi over here. This one. Similarly, I'll delete this. This also here. So now let's run this and let's see the scopes once again. So you can see that whenever I have given a step input of any of the so this is your step input in purple, and this is the dynamics that is behaving. So it is going uh, exponentially. That is not desirable. So what we are going to do is we are going to uh, design the PID controller over here. So for designing a PID controller, I already so you have PIDs over in commonly used block itself. It should be there. Signal attribute, math operations. Okay, yes, this is the PID controller. So which I'm going to place in between. So what is the philosophy of using PID is uh, you are going to get the error from the output and your reference signal, and this error you are going to feed it to the PID. So I have already made the plant for you. This is my plant. So let me show that over here. So this was our usual plant, but here what I did, I have introduced a PID. This PID is taking control to stabilize the system in order to, the philosophy is it is taking the output signal as a feedback in minus, and it is taking the reference signal and it is going to give an error, and based on this error the PID will act on autonomously. Same in similar fashion, three PIDs will be needed because we have three outputs. So once I run this plant, let's see what happens. So now you can see the system has been stabilized. You have given step input. You are or approximately you are following your command. In Z, in phi also approximately you are following the command, and Y also you are approximately, although you have some oscillations over here, but you are following your command. It means your plant has been stabilized. It means you have instructed it to go to certain step and then stop or do something, and it is following whatever you have given the command response on. So yes, I agree that this particular lab is uh, not possible to cover all the aspects in one lab, but yes, this lab will essentially give you a flavor of uh, the autonomous controls of robots, your flight controls, or maybe drones, or your actual aircrafts, helicopters, all sorts of flying things. Not only dynamical systems, you can have uh, robotic arms that essentially used in your industries. You can actually make um, the virtual dynamical system over here. You can actually simulate it, whether it is working well or not. Then you can further go into your design part. So yes, that's it from my side. And we have already shared the manual with you. And you can actually write out with other inputs and forces and moments. Okay, thank you.